Hello, I'm Dr. Ron England, and welcome to Probability and Statistics for Engineers. I'm going to get you started. This lecture is not just going to be about the class, it's also going to get you introduced to the beginning of probability theory, but I kind of want you to know what this is all about. First, you're not going to go out and memorize a ton of equations. That's just not what you do in this class. We're going to talk about practical use of probability and statistics to solve real engineering problems. And to that effect, you're going to need to use all the tools available to you that we're going to use in this class. Tool number one, Python. And really, specifically, the Python libraries like NumPy and SciPy, and the statistics and plotting, because visualization is important, to be able to do good work with statistics and probability. Now, in this lecture, we're going to talk about what you're going to use them for. We're talking about a lot of theory, but also talk about another tool you're going to use, which is AI. You have a number of great AI tools. So you can either spend a ton of time trying to figure out how to put together code and debugging it to plot something, or you can just go to an AI and say, here's the data, give me a histogram, give me a box plot. Now, it may ask you for some other parameters, and you need to know all about what those parameters are. As far as assignments and stuff goes on, you're going to have a weekly discussion. You're going to have a bunch of quizzes, which I keep open all the time. And you're going to have some assignments, which are actually formal engineering reports. And as anybody who's ever had me for class knows, I am a stickler for being able to write a decent engineering report. There's a reason. You're going to be judged by how good your engineering reports are. But with those things said, let's get into this. So we're going to talk a little bit about probability theory. And I'm going to kind of get into it. I'm quite sure by now you've probably read some of this, so we're going to kind of move on to the next slide. Now, definition. Probability is simple. Things have a probability of occurring between 0 and 1, okay? Or between 0% and 100%. Things do not have a probability of 110%, and they can't have negative probabilities. All the things that deal with how you use probability, and it's used everywhere, are described by mathematics. And there's a number of axioms that are just, and these should be things that should make sense to you. So, for example, you can't have negative probabilities. That just doesn't work. And okay, if you take all the sums of the probabilities and put them together or something, they should add up to 100%. And you have the ability to add probabilities for mutually exclusive events. These are just basic axioms, and a lot of this is just really common sense. And if you think about it, you can just use examples to do that. Like if you roll a dice. It's a six-sided die. You got 1 out of 6 of any given number. Or, picking a number out of a series of numbers, of integers, 1 out of 2. Okay, these are pretty straightforward things, and I think a lot of it's going to make common sense. And what we really want to do is to have a lot of the stuff that we go over this class make sense to you, especially as we get into the more complex things. Because there are some complex things. We're going to talk about a little bit of it in this lecture, but not a lot. Now, the sample space is the complete set of all the possible things that can happen. Some of these are really simple. Like if I say, here's a deck of cards that has 52 distinct cards, okay, the sample space is the deck of cards. Sometimes the sample spaces are much bigger. We're going to talk about the bigger sample spaces later because we're going to talk about the population and the sample, which are two different things. And that gives you a lot of what we have to deal with when we're actually trying to figure out how to use statistics to solve problems. Okay, we have different types of events that can occur. Okay, simple event, rolling a die. That's a pretty simple event. You get a number, done. Okay, an impossible event is something that cannot occur. Now, compound events combine more than one simple event. So in other words, if I roll a 2 and I say after I roll the 2, what's the probability of rolling a 6? Well, the probability of rolling a 6 is still 1 out of 6 after you've rolled the 2. But what's the probability of rolling a 2 and a 6? Put that compound together. That's 1 out of 36, by the way. And then you also have things that are certain events, like rolling a number between 1 and 6 on a die would be certain. Okay, again, I don't think there's anything tricky here. Now, you can do all sorts of types of thought experiments when you look at actually how to calculate different kinds of events with just a simple coin. Okay? Like if I said you've got a coin, you flip it 15 times, what's the probability of 5 of them being heads, which is the same as the probability of 10 of them being tails? Okay? Or what's the probability of it being heads, tails, heads, heads? A specific sequence. Okay? Those are two different types of calculations, and you do need to know how to do them. This is not what we're covering right this minute. You're going to do that later. Okay? And then you've got things that are, you've got to consider like a mutually exclusive event. Well, again, easy example. You can't roll 2 different numbers on the same die with one roll. They're mutually exclusive. Okay? It's either going to be one or it's going to be the other. Okay? This does make a difference in how you calculate, how you use this. Now, different from mutually exclusive is independent. And a lot of the events that we deal with in statistics are independent. In other words, the occurrence of one event is not going to affect the probability of the other. Again, very simple. If I roll a 1 on the first roll of a die, and then I roll the die again, well, does the 1 on the first roll have any effect whatsoever on the second roll? No, it does not. The probability of that 1 on that second roll is still 1 out of 6. You put the two probabilities together into a double to both. Yeah, it's 1 out of 36, but that's not the same as saying that second roll is not affected. That second roll is not going to be affected by the first roll. Okay. Now, don't confuse independence and mutual exclusivity, because the reality is, in many cases, independence and mutual, if you have 2 dependent events, a lot of times they could actually be mutually exclusive, but they're distinct and different concepts. Okay? So if you read here, which I'll actually read this to you, in fact, events that are both non-trivial, probability greater than 0, and mutually exclusive cannot be independent because the occurrence of one guarantees the non-occurrence of the other. Okay? In other words, if you roll a head, if you toss the heads on a coin, or you flip a coin with the heads, and it means it can't be tails. That makes them pretty dependent upon each other. Conditional probabilities, that's a really simple statement too. Hey, if A occurs, if you got something that occurs, what's the probability of this occurring given that that occurred? Well, we talked about the die examples, but hey, that didn't work because those are independent. In some cases, the probability of something occurring is dependent upon the other one occurring. And this is not really hard to come up with an example. I've got a deck of cards and I pull out one card, okay, and this is something, okay. The fact that that occurred actually has an effect on what I can draw the next time. And the reason being is that the deck has 52 cards and I pull one card out and it has a chance of 1 of 52 of occurring. Another card is going to have a chance of 1 of 51 occurring because the deck doesn't have as many cards. So the probability does change. Okay. Now, we're going to talk about Bayes' theorem in a lot more detail later. But the classic case of Bayes' theorem is a simple one that is used all the time. If let's say the probability of the actually occurrence of some sort of sickness in the population is 1%, and you're tested for that sickness, but the accuracy of the test is 90%. In other words, it's wrong 10% of the time, right 90% of the time. When you get that test and you're shown that you're positive, which is a 10% probability with the test, what's the real probability that you actually have that disease. You would say, well, the test is 10% accurate. Okay, therefore, is a 10% chance. I mean, it's 90% accurate. There's 90% chance that I have that disease. Wrong. That is not true. Just because a test is 90% accurate doesn't mean there's a 90% chance that that one test definitively says with 90% accuracy that you have that disease. We're going to go over this, I know, and right now everybody's going, what? What? That doesn't make any sense. Yes, it does. Now, I gave you something very classic, okay, that the incidence of it in the population was 1%. Okay, inaccuracy in the test is an important thing, and Bayes' theorem covers that. Okay, we're going to deal with Bayes' theorem later because that's actually part of one of the lectures. So you're going to get to see this a little bit more. But that's another thing. It's like, wow, it's a little bit more complex many times than, you know, what. And by the way, Bayes' theorem is always why you should get a second opinion, just so you know. Law of total probability. Okay, you take all the conditional probabilities and you simulate them all together and you get the total probability. We're going to deal with this one, but again, we're not really dealing with things that aren't things that just make common sense to you. But don't take common sense into meaning easy, because many times the calculations to figure out the total probability of other events that have specific conditional probabilities can get pretty complex. There's some mathematics involved. I'm not going to have any one of you required to sit down with a piece of paper and a pencil and a calculator and calculate out these types of things. We're doing this in code. You're going to be programming in Python, and the libraries do handle a lot of the really just, you know, tapping on that calculator. Okay, now, all that said, we're doing this for engineering, okay? So I'm going to talk a little bit about the biggest thing in engineering that we typically use statistics for all of the time, engineering reliability, okay? We need things, we design things, we build things to perform their intended function, and that means without breaking. But things break. You live in the real world. Things break. So we have a lot of these types of metrics that we use and statistics that we use to figure out what's the probability of breaking. And if you know the probability of breaking, and you know that you can actually do things called maintenance to solve this problem of them breaking, hey, we can figure out how to optimize the system for the costs of failure. And that's important. Now, reliability does get a tad bit complex. Not terribly, though. So if you're looking at, say, multiple components, all of which have to work for the system to work, and each component has a probability of failure. Let's say they're all 90%. Well, does that mean the probability of failure of the system is 90%? Sorry, no, it is not. It is more than 90%. Because the failure of any one of those, which is 10%, okay, and I'm saying that the probability of non-failure is 90%, but now you've got all those adding up. They're actually, yeah, so we're going to do this too. Guess what? It's going to be more than the failure of any given component, because the failure of any given component causes the whole system to fail. Okay? We need to take this into account when we deal with designing reliable systems, especially if we've got systems that are in series and have a system failure associated with the failure of any one of the components within that system. Once again, I'm going to say we're going to cover this in more detail, and we're going to figure out how to do this. Now, I'm not going to talk here about reliability distribution models. The only reason this is here is so that you understand that we actually create these things, mathematical constructs that characterize the numerical properties of these types of systems so that we can calculate failure and probabilities of different types of events occurring. So exponential, Weibull, and normal, the three that you see here. And I should probably put them in different order because normal is the big, common, you can't say gold standard for distributions, but it's the one that a lot of stuff follows a normal distribution. And we can characterize it with just simple mathematics, simple numbers. And again, I'm not going to have you sit down with a calculator to do it. We can plot these, we can put points on them, we can figure out where we are on normal curves very easily with writing very simple code in Python, because it's more than just saying here's the number, it's the visualization of the entire system, which definitely means that you're going to be doing plots. So, where do we use this in engineering? Well, here's the bottom line. I got a whole bunch of examples here, but the reality is everywhere. I'm looking at this particularly important in manufacturing engineering. So manufacturing engineering is where we're going to use a lot of our examples, but I also want to have a lot of fun with just, because we don't have a manufacturing plant here to use real data from. We're going to use numbers from different data sets that I thought were interesting for you guys being able to do the analysis. Because the reality is I want to make this class enjoyable, but more importantly than making it enjoyable is I want to make it practical to the things that you would be expected to do and how to use statistics to get real answers to solve real problems in engineering. And with that said, I'm going to call this lecture done, and you're going to have a whole bunch more. But I think everybody that's taking this class will really enjoy the approach that we're taking to doing it and producing the real world type of stuff that I'm expecting us to do. Thank you much, and hope you enjoyed this 18-minute long lecture. I'm long-winded on this one, but yeah, sometimes it's just that way. Sorry.